So we saw in the last section that when molecules fragment, it's often very logical and makes sense. Other times it's not as logical and doesn't quite make as much sense. And so we're just going to take a look at some weird fragmentations. Overall, these are not going to be that useful. We'll have better ways we can identify these functional groups. But all the books show this, so we're going to go ahead and just learn it, but it's not really going to be a main thing. One of the weird things that fragments are alcohols. And alcohols are so reactive to this fragmentation and rearrangement that most of the time you actually don't see your molecular ion peak because it fragments so fast. So if you Google the mass spectra of some compounds that contain alcohols, oftentimes you won't actually see your molecular ion peak. I'm only going to use examples where you can see the molecular ion peak. I'm not going to try to kind of trick you and give you a mass spec that doesn't indicate the molecular ion peak. And so the first type of fragmentation it can undergo is alpha cleavage. And so here, when we bombard our compound with electrons, instead of taking the electron out that has a bonded to something, we're actually going to take out an electron in one of the lone pairs, right? And so we have a cation here. You can tell we're missing one of our lone pairs. And so what happens during this fragmentation is a radical rearrangement that causes this bond to break. And if you think about your products formed, you'll get this protonated carbonyl looking thing, and then some kind of radical to this other side. For us, it's not that useful. Another thing that can occur is dehydration. And so again, we have this radical. And basically what it can do is just undergo a dehydration to form an alkene. And then our water molecule. This water molecule is not detected. Because it doesn't have a charge. However, this alkene is detected and it'll have a mass minus 18 peak, right? So it'll be 18 less than your molecular ion peak. But oftentimes it's not a very actually huge peak from what I've seen. And so it's again not that useful. And if you're identifying an alcohol, IR is going to be easier to use anyways. So overall, it's not all that useful, but just something to keep an eye out for if you're Googling the mass spec of certain compounds and you don't, and its mass doesn't correlate to its molecular ion peak, you might have some kind of weird fragmentation and rearrangement occurring. Amines are also similar. They'll also undergo this alpha cleavage. So if you're looking for compounds with amines, their mass spectrum might look a little bit funky. And then finally, ketones and aldehydes. They undergo what's known as a Mclafferty rearrangement. And so what occurs here is, again, our radical forms on our oxygen instead of breaking a carbon-carbon bond. And then we get a whole bunch of radical reorganization, right? So we form this OH bond. We form a pi bond down here. And then our radical kicks down over here. And so it'll form this compound over here, which comes from this left side. plus this other complex, which has a radical, which can undergo keto-enol tautomerization. And again, this is actually not that useful either. None of these really are, but the book goes over them, so here they are. I probably won't ask you really any questions about this.